Okay, guys, I'm going to try and get through this. I'm getting pretty tired, actually. Okay, definite integrals. So that's what we're working on before when we were learning about how to find the area under the curve. I'm going to give you some notation now. When you want to find the area, we're going to under the curve. This should be the area under the curve. It's going to be written as an elongated S. Think about taking the sum, you know that as the sum, and we're going to use it here. Now, I'm going to show you this part. You don't really need to know it, but I want to show you where this is coming from. Remember I said if you divide up those rectangles into itty bitty little pieces, it's like taking a limit and you're going to spread out, and I'll put this back under here. If I were to divide this up so small and make these rectangles so small that you couldn't even slip a piece of paper between them because they're so tiny, it's like taking infinitely many rectangles and putting them underneath this interval. It's like taking a limit as you approach infinitely many number of rectangles. Here's how you would write that. And if you take calculus in college, you're going to see it written this. You will have to do it this way. The limit as n approaches infinity of the sum, I did not leave myself much room here, of I equals 1 to n of f of x sub I. That just means we're going to take f of 1, f of 2, f of 3, f of 4. We're just going to sum these up as we go. Delta x, the change in y. Okay, it's the limit of the sum, and the change in y is that interval. Remember it said divide up into equal subsections. That delta x represents the equal subsections as you're going on. Okay, we are not going to explore this. We did enough limits at the beginning that I feel like you have a concept of it. That's all for this class I need you to have, is just an idea that a limit is getting really close together, as close as you can possibly get. For this part of the class, though, we're just going to say the area under the curve is represented by adding, and this right here is going to represent the sum, by adding an infinite number of rectangles together from A to B of f of x. Oh, there's a little bug on my paper. Do y'all see him? Hello, little bug. You want to learn some calculus? Okay. If you like bugs, I'm really sorry. I don't. Okay, bug's gone. Of f of x, and some of you are like, oh, Miss Dean killed a bug. I probably did. Of f of x dx. Dx is our change in x. Okay. Now, one of the things I did on my paper is I was learning this, going back and like way back in the day. I wrote this. I wrote that this symbol, the integration symbol, is going to be adding. It kind of helped me understand what I was looking for. Adding an infinite, hope I spell all that right, number of rectangles together. And the dx, adding up all the rectangles with height of f of x and a very small width from A to B. I'm sorry, not dx, but this whole thing in here. Adding up all the rectangles with height f of x and a very small width. That's the dx part. From A to B. Okay. And most of the ones we're going to do are going to look just like that. Okay, so let me give you kind of one more little, oh, there's my black. Let me give you a little scenario here. Let's say that we're going to give you a curve, and we're going to find the area under this curve. I'll give you a second to kind of look at how mine looks. I'm going to go from A to B, and we are going to find the area under that curve. Okay, so when you look at it, you might think, well, it's kind of sort of, I could maybe draw a rectangle and figure something out, but I can't. So here's how I would write this. This is what this would represent. Underneath here, I would make those rectangles. I would try to anyway. And I would take y dx. This is what I would be doing. I'm finding the area under the curve from A to B of this function here. This is y dx. Okay, adding up all the rectangles with the height of f of x, or y, and a very small width of dx. One of the notes here that I should say is that when you go to take the integral, we are only going to be doing this above the x-axis. You can't do the integrals down here. Okay, we are only going to be doing integrals up here. Later on, you can do them other place, but yeah, we are just doing them up above. You know what? Let's actually put that here. Note, function must be above x-axis. Must be above the x-axis. Okay, so let's actually do some of these. Now that you kind of know what the notation's going to look like, let's take a look at this. All right, describe the geometrical meaning of the integral from 1 to 4 of 2 dx. All right, so let's graph it. All of these, almost the first thing I would tell you is draw it. When we were doing stationary and optimization, draw it, draw it, draw it, draw it. Okay, y equals 2. That's the function. What does y equals 2 even look like? Well, I'm pretty sure it's a constant, it's a straight line, it's a horizontal. It looks like this right here, y equals 2. That's y equals 2. We only want to look at the integral from 1, 2, 3, 4 to 4. So we want to look at the area under the curve of that right there. Can you tell me the area of that? Yeah, that's pretty easy. Area equals length times width. If you got 6, you're right. So the area equals 1, 2, 3 units of the length, and the width, well, that's 2, so 1 would be right there, so that'd be 2. So that would be 6 units, whatever they happen to be. There you go. That's all you're doing. Are they all going to be that easy? No, of course not. It wouldn't be calculus if they were. All right, let's try the next one. Describe the geometrical meaning of -1 to 2 of x plus 2. So we're going to start off, we're going to draw it. We're going to graph it. X plus 2. All right, so x plus 2. So 1, 2. 1, 2, 3, 4, 6. Okay, that'll be good. Let's see, I'm going to go from -1 to just 2. 1, 2. So I'm doing a very small area right here. I probably should have drawn it a little bigger. X plus 2. So if I plug in 1, I would be at 3. So 1, 3. If I plug in 2, I'll be at 4. Try and make sure I get a little bit straight. If I plug in -1, oh, I should be at -1, 1. Okay, yeah, that'll be right. Okay, so I'm going to get my red out. I'm going to draw it. Okay, and then I need to find the area under there. Ooh, what do y'all think? I need some geometry people to jump up and yell like, we could do this. Okay, so here we go. I'm going to rewrite. I've already got this. I'm ready to go, but I don't know what to do. I need to find the area under the curve. So you might look and go, well, could we do a trapezoid and a trapezoid? I mean, maybe. What if I draw a line? This is -1, 1. That's 0, 1. And right there. I could probably find the area of that box. And hey, that's a triangle. Okay, so let's do this. Let's do the area of the triangle. And let's do the area of the rectangle. Okay, I'm going to give you just a second to kind of think about it, and then I'm going to label some things. And yes, it is a right triangle. What I know on the base here, that this is 1, 2, 3. So on the rectangle, I know the length is 3. And I know the height is, let's see, this is 4, 3, 2, 1. So that's also 3. So this is 3, and this is 3. The height here is 2. Oh, I did that wrong. Wait, is that right? 3 times, oh, my back. No, that's not right. Area, 1/2 base times height. The triangle is 1/2 the base times the height. Okay, so that is right. I did my what do I want to say? It's 1. 3 times 1. That's not 2 right there. When I said that, I'm half asleep, y'all. I need a nap. It has been a long week. 3 times 1. Okay, there we go. Okay, that's going to be 3 times 3 is 9 divided by 2. I'm going to leave it as a fraction. 3 times 1 is 3. So the area under the curve would be 9 over 2 plus 3. Okay, I'm going to do some real quick math here. 9 over 2 plus 6 over 2, that would be 3. So 9 and 6 is 15 over 2. I could have used a calculator too, it would have worked. Could have done a decimal, 7.5 if you want to do that. That's fine too. But you kind of get the idea with integration. It's not super hard. You just have to be able to find you some geometric shapes. Now, yeah, they're going to get harder and it's not going to be as easy. Okay, so this is a check for understanding. And I know that it is misnumbered on your paper as well as my paper. So no worries on that. It's like in a completely different spot on mine somewhere. I'm going to give you just a quick hint on this. And I'm going to tell you that when Miss Dean worked this, she might have gotten into the law of cosine, and I really had fun working this. It was quite challenging, but I'm just going to tell you, you do not have to get that dramatic with it. You can actually assume some things. So on this one, you're going from -2 all the way to 3. So you're going to find the area under the curve of all of that. Obviously, you can already see that you can draw this line right here. Okay? I'm going to let you try and figure out the rest. You're trying to find the area of this, so you know you can use 1/2 base times height. And you need to find this right here. But let me remind you, when you do 1/2 base times height, here's your base. You can see your base is 1, 2. Your base is 3, right? What is the height? Because that's what I totally missed. You can just look at it and see how tall it is. And if you're thinking from here to here, you would be correct. Okay? 1/2 base times height to find the area of the triangle. You can find the area of this, and then you're going to work it from -2 to 3. And you're going to, I think you take a picture of this and you load it on your, on Canvas so that I can see you did it on that one. Okay, and I'm going to stop right there on this short video.